Welcome to our multidisciplinary design project. We are Group 12 and our members are Andy, Dan, Eugene, Jamie, Tarun, Ridwan, Haoguan, and Junyan. This is our agenda for today. Here's a demonstration of our beloved robot striving its way through the task. Now let us take a deeper dive. Here's a so, how does our project work? The Raspberry Pi is a center for communication. It communicates with the Android application via Bluetooth, with the STM32 and sensors via wire connection, and the algorithm and image recognition algorithm via Wi-Fi connection. The algorithm is also hosted using Python Flask. For the task, the Android sends and command an arena details to the Pi. The Pi will then send the arena details to the algorithm, where the algorithm will plan the fastest route and send back the route details to the Pi. The Pi then communicates with the STM32 and starts moving. If the camera and its sensors sense that there's an obstacle, it will take a picture and send back to the Pi for analysis. The Pi then communicates with the image recognition algorithm to analyze the image taken, and will send the ID back to the Pi, where the Pi will send back to the Android and display on the map. Now let's take a look into our Raspberry Pi and hardware. The hardware used is Raspberry Pi, STM32, ultrasonic sensor, camera, and the robot parts. The different sensor and wheel control are connected to the STM32 directly. The STM32 will control the movement of the wheels, process the data received from the sensor before passing it to the Pi. From the log, we are able to see the commands and data received by the Pi. Our team uses an A-star algorithm for our pathfinding. Here are some details of the algorithm. It uses a graph data structure. It's an extension of the Dijkstra algorithm with heuristic functions. The worst case complexity is E log V, which is considered efficient among the other pathfinding algorithms. We chose this algorithm because it guarantees the shortest path for our robot to move between obstacles. Our algorithm has a main solver class that handles the calculation between the coordinates and the state of the obstacles, whether it's visited or not. It also calculates the safe cost based on the proximity of the other obstacles. The class will then determine the route to navigate based on the distance and the safe cost. Even though A-star algorithm is rather complete, rigorous testing and optimization is still required for the best results. Details such as the different degree of turn, speed, and rotation of wheels, change of directions to find the correct facing of the obstacles were the challenges for the algorithm. Although the A-star algorithm finds the fastest path, it does not take into account the angle and the rotation of the wheels. The robot is not able to turn at a fixed position, thus when it's moving to the next obstacle, the robot might exceed the boundary or knock onto other obstacles. The vehicle demonstrates awareness of obstacle location, but employs a static approach to changing direction. Unfortunately, this fixed methodology leads to a collision with obstacle during a directional adjustment. After adjusting and implementing a safe cost into the algorithm is able to evaluate the path to ensure collision-free during the change of directions. So, what did we use for the image recognition? We use the YOLO, you only look once, due to several reasons. It's fast and lightweight, easy to use, decent accuracy, quickly adopted and with lot of documentation. It also uses RoboFlow site, where we can quickly annotate on images, increase the complexity of dataset with extra pre-processing and augmentations. Though the new version performs better, GPUs such as the NVIDIA RTX 3090 is lower than the version 5 on lower tier GPUs such as the GTX 1650 Ti. We also tested on the version 4, however it has an error rate of 2 in 10 images. The version 5 were able to recognize all 10 images without any error, having a 25% increase in accuracy compared to the version 4. For our dataset, we used 15,000 images with varying brightness, hue, angle, and quality. The version 5 model is able to recognize images placed 20 to 50 cm away and tells the robot which direction to move based on the arrow recognized. Now, let's take a look at our Android component. It's split into two main parts, the Bluetooth and the GUI. During the testing for the Bluetooth component, we were able to communicate between the AMD tool and serial communication tool to the Pi and the tablet, but not directly between the Pi and the tablet. This was due to security and Bluetooth version disparities. To resolve this, we changed the security testing and updated all components to their latest module. For the GUI, we implemented a drag and drop function for obstacle placing. And to improve our user experience, we implemented a just tap on the obstacle to change the directions it's facing. To make full use of the limited screen size, we adopted a bottom navigation menu with 3 fragments.
There were 4 main challenges faced during the project: lighting, high battery usage, integration, and time management. Firstly, different brightness and lighting caused different results for image recognition and ROM analysis. To resolve the issue, we increased our dataset from 10,000 images to 15,000 images with varying brightness. Secondly, the robot consumed high power and required consistent charging, which delayed the testing and sensors accuracy. To tackle time management, our team had good planning and split the workload evenly. While some were working on calibration and refining the robot, the rest of us worked on the robot. We were also able to successfully integrate all the components together despite the challenges mentioned before. Here are some things we have learned from doing the project. We have learned how to apply the scenarios faced by the robot to real-world situations, learning how driverless cars may tackle the complexity of real-time scenarios, such as environmental uncertainty, obstacle unpredictability, algorithm precision, and optimization. To solve this, large data training is required. The model learns from extensive datasets covering diverse obstacles, vehicles, and traffic controls. These were our overall task contributions. In conclusion, for this project, we have successfully completed the requirements in the checklist, task 1 and task 2 during testing, get experience on how different components are integrated in the real world, and we had an enriching experience on developing the robot. We hope that future generations improve on the development and create a more holistic robot.